Hello and welcome back to the Inspired AI series. I'm delighted to reintroduce our final speaker and our final session of the day. Please do welcome on stage Fabrizio Silvestri, who's a research scientist at Facebook AI, who will be presenting on how decoding strategies affect the verifiability of generated text. Fabrizio, welcome.
Hello.
Hi, the stage is yours.
Thank you very much. Let me share my presentation. Start it. Cool. All right. So first of all, thank you for inviting me. It's really great to be here. Sorry, we had some technical issues when we had to start the presentation. I don't know what happened. Computer science is not deterministic, as my presentation is going to actually, kind of show. In fact, this presentation is about a quite technical aspect of automatic text generation, and in particular is about deciding when the generated text is actually factually correct. I'm gonna explain to you in a second what we did, but let's start. Let me first start by thanking the whole team that is behind this work. It's let's say a fantastic team of people at Facebook AI, and in particular, the first author is a PhD student that was intern in our team last summer. So I'm going to start with a quiz. Usually, this is better when it's interactive, but just for your own amusement, these two columns here are, let's say, two pieces of news, more or less on the same topic. The difference is that one has been generated by a computer, the other one is being written by a human. So I would like to ask you to try to guess which one of the two is actually being written by a human and the other one by computer. Of course, you're not going to reply to me, but just take 2 seconds to try to make a decision. And if you have answered that the second one is fake, you're right. But if you look at the quality of the text, is really impressive. Let's take another stab at it. Try to understand. Try to guess which one is fake and which one is not. Again, as you can see, there are few hints maybe that you think you have captured, like septe instead of sept. But unfortunately, the fake one is the second one, which looks better, but and the first one is being written by a person. And if you want to make things more difficult, you can actually ask just the question if this text has been generated or written by a human. This text is fake, so it's been generated by a machine. This one instead is true. I mean, again, I don't want to take too much time, but it goes on. And in case you're not scared yet, this is a... Sorry. Okay, so what's the recipe behind the generation of text? In natural language processing, we adopt these, let's say, technology or these, let's say, thing that is called language models. And a language model is a very simple entity, a mathematical entity, and it's basically a probability distribution over a sequence of tokens. So you want to estimate what's the probability that a given sequence of words has been generated by a language. So, like, even without going into too many details, this probability distribution should be able to capture the concept that the cat is on the table is more likely to be correct English than the cat is on heaven. Eye in the sky should have a probability much, much higher than that sequence of blurred text that maybe can be read as high in the sky. But now, one interesting question that you can ask regarding language models is, are they able to catch, let's say, correctness of sentences? So, for instance, in this case, Dante was born in Florence versus Dante was born in Pisa. Which one is more likely? Well, we know that Dante was born in Florence, but the two sentences are both correctly formed in English. So it's not clear which one should have a higher probability. So, during this year, there's been lots of work, and in particular in the last couple of years, there's been a lot of work in making language models more intelligent and more semantically aware, and also capable of, let's say, containing some knowledge. And let's see how good they have become. So to understand what a language model is, I mean, we would require lots of, let's say, maybe a complete hour. But given that currently the modern language models are the so-called neural language models, I just want to make a remark of the first neural language model that was proposed almost 10 years ago by Tomasz Mikolov in his PhD thesis. And basically there you have an input that represents word, and now you want to predict which word comes next more likely, or comes before more likely. And all of these possibilities are possible in training these kind of language models. And all in all, you end up with a representation, a dense representation that is captured by the ST component in the picture, that it's much shorter than, let's say, a vector of 1 and zeros, but still retain important information about the word. And in particular, that representation is able to capture other properties like semantic similarity and stuff like that. And that's the basis of all the methods that are used to generate text. So for instance, this is one of the first mechanisms that was used to generate text. And it's basically based on a recurrent neural network, and it's called an autoregressive text generation mechanism, because you start with a start token that you can see in the picture, and then the model takes as input the generated next token, and it continues like that. So it never takes any input by the user; it automatically generates texts. And of course, this is where chance comes into play, because at each step in text generation, you're actually generating a distribution of a probability distribution over a vocabulary of text. And it's exactly that distribution that is the subject of the text generation mechanism. So basically, how you sample the next word from that distribution is the key. Now, everything that I've explained so far looks pretty complicated, but the scaring thing is that you can actually build that system using modern, let's say, frameworks like PyTorch in possibly 35 lines of code. And this is pretty scary, because it can really generate good text with a very few, let's say, I mean, you can generate good text even if you are not the best engineer in the world, which is kind of scary. I just want to also maybe recall a bit the concept of attention. That is something that was developed 5 years ago in the context of neural machine translation. There, basically, the machine translation mechanism is when you have an input sequence of tokens and you want to output a sequence of tokens in a different language. The mechanism of attention is basically helping the decoder, so the part that is trying to generate the translation, by saying, okay, this token depends on these input tokens. So, for instance, in the case of translating English into French, you can see that in this sentence, when you translate distraction, when you translate la destruction, you actually are translating into distraction. So when you generate distraction, you have to pose your attention in la destruction. So basically, you see that in these metrics, the color of the pixel determines how important is the things on the row to decode the things on the columns. So this actually this attention mechanism is at the basis of what is being referred to as the NLP Muppets revolution. So why Muppets revolution? Because the first models that were using attention as the mechanism to generate text were called with names like Elmo, Bert. So those are characters from Muppet characters, and so that's why we almost always refer to NLP Muppet revolution. So this NLP Muppet revolution is also usually referred to as the ImageNet moment in NLP. ImageNet was a breakthrough in computer vision, basically pre-training on a huge amount of pictures helped all the classification tasks in computer vision. And the same happened in NLP. Once we had a good way, by means of attention, to pre-train representations from large corpus of text, we basically saw an increase across all the various text classification tasks that were proposed. So this is a huge breakthrough. And then basically modern NLP is based on these kind of things. And these are the architectures that are popularly used nowadays. GPT, then GPT-2 and GPT-3 are actually variations of the same model. And if you have followed let's say the news lately, you can see that GPT-3 is actually the latest guide that has been proposed, and it really shows impressive results. But let's say, and this is the common denominator. This is called transformer, and as you can see, it's extremely, I would say, extremely simple. I mean, it might look scary. I can tell by looking at the pictures, but once you start looking at it, it's extremely simple. Basically, it's a self-attention mechanism. So when you have a sentence, you compare all the tokens in the sentence with the other tokens in the sentence. And you want to build a probability distribution for each token, saying, okay, for token TI, these tokens, I mean, in the rest of the sentence are important, are very related to that token. And this way you build a matrix. In fact, you replicate this matrix, and you apply some tricks that you can read in the paper if you want. But this is really it. So it's a gigantic matrix multiplication, and that's it, which is a huge difference with respect to what it was present in the past, like recurrent neural networks, because training those networks took lots of time. It was not easily parallelizable. It was even difficult to implement. So this is a huge leap in terms of modeling that is actually at the core of the NLP Muppet revolution. And as I just said, you basically, through transformers, you self-attend to tokens in a sentence. All right. So now, once these transformer models were proposed, people started to ask questions, non-trivial questions. So if you remember the example that I was making at the beginning, we were asking whether this new language model can basically simulate a knowledge graph. A knowledge graph is basically a huge data structure that is mostly manually built. Wikipedia is the typical example of a knowledge graph. Instead, if you want to use a language model, you just read text and you try to see if the knowledge graph was actually inferred. So the typical query in a knowledge graph is the one that you see over there, Dante born in X, and you want to replace X. In the case of a neural language model query, you see Dante was born in, and then you add a special token called mask, and you want to generate the replacement for mask. And you hope that the language model will generate the right replacement. In this case, some of my colleagues showed that transformers are very, very good at it. So you can see some examples over there. So the first half basically is, trying to fill in the gap. So Francesco Bartolomeo Conti was born in Florence. It's a correct answer. and it is actually returned on top by the method, and so on and so forth. And also, when you actually add more context, like you specialize the question for a given concept, like at location, you are likely to find an overflow in a, and then the correct answer is almost always on top. So this is very good. So it means that, well, it seems to mean that language models can capture knowledge. Now, there are ethical implications, as you can see, and GPT opened the way by saying, okay, we have this model, we are not publishing it. And actually, even GPT-3 is behind the license, so you have to pay a license, and you can actually look at the release strategy. This lasted not too long because other companies actually trained the language model and put them online, and now you can use those language models almost for free. I would say for free. So getting back to text generation, we said that you have to generate the next token from a distribution of tokens. And there are several generation strategies, and all of them has pros and cons. Again, the simplest one is to basically always take the most likely token. But why stop at that? You can say, okay, I take the top K and then I choose randomly between the top K. Or I take some subset of them. Or there is a better strategy, which is you keep K sentences among those that are the more likely generated by the model. And then whenever you generate a new token, you compute how good the sequence up to that token was, and you again keep the top K. Actually, we observed something during our study, which is the first one tends to generate very good let's say text. The second one tends, like likelihood based, tends to generate correct text, but it generates repetitions. So we simply adopted a hybrid approach called delayed Bing search, which is basically consisting in generating the first L tokens using top K, and then we use Bing search. Again, this is a representation of Bing search, but I don't want to spend too much time on it. In case you have questions, I'm happy to take them afterwards. So here's our system. So we designed this system to assess how good text generators are with respect to verifiability of text. So the idea is the following: you take a text prefix from Wikipedia, and you ask your method to continue to generate the remainder of the text. And then, sentence by sentence, you try to understand if that's factually correct. In order to do that, we used off-the-shelf fact-checking mechanism. The one that we used is the best fact-checking mechanism as reported in the Fever workshop. Fever is the dedicated workshop to automatic fact-checking. So you cannot do better than this in an automatic way. And so we use that. And then on top of this, we built several evaluation metrics. One is supports per generation. Basically, for each sentence, we see if the fact checker was able to say, yes, I can say something about it. And then actually, we looked at how many sentences were true out of those that could be verified. That's a supports per verified. And in the example here, you can see that we verified 3 and 2 of them were supported, true. And then, I mean, to also measure what I was saying before, that is some sentences are repeated, we actually took the same metrics, but by eliminating duplicates. So basically, we eliminate duplicates and we consider like how many of them are supported and how many of them are verified. In addition to these, we also measure the syntactic quality of the, let's say, of the text. This is the second column in the results here. And as you can see, let's say, from the syntactic quality, as I was saying, the syntactic quality sees that sampling techniques of K are better, so they tend to not repeat text. On the other hand, the Bing search is very good at generating verifiable text. And yes.
Hi, Fabrizio. I'm so sorry to jump in. We are slightly running over time at the moment, so we'd love for you to continue your presentation in the Q&A section. So we'd love to invite yourself and everyone watching to just click through to the link that our lovely team are going to place into the chat, where you can actually continue the presentation and take some interactive questions from our audience.
Yeah, it was basically over. So
I'm so sorry to have jumped in. Thank you, Fabrizio, on behalf of everyone here today. We really appreciate your time and your presentation. Well, what can I say? It's been a hugely informative day, and we very much look forward to seeing you all again at the next Inspired AI session at 3 p.m. Central European Time on the 8th of October, where we have our first AI in Action Day. But for now, head over to the sessions area of the platform, where you'll find our networking lounges open. We have Joel Mayer, who's a social disaster manager from the Pacific Disaster Center, hosting a networking session for you guys this evening and sharing the results from the polls that have taken place throughout the afternoon. You can use the chat on the right-hand side to start a conversation, or click the participate button to share your audio and camera to go live on screen with Joel. We can have up to 9 people on screen at a time, so we hope that you appreciate that. If you want to start a topic of your own, you will also be able to create your own subgroups. Simply click on the plus add session button in the top right-hand corner, complete the details, and your session will appear. Invite people to join by posting into the networking lounge or in the event chat. Feel free to create groups based on topic, industry, geography, whatever you like. Be sure to add yourself on our Tech Talks WhatsApp group to continue networking post-event. Simply head over to the sessions area, scan the QR barcode, or enter the lounge and click on the link to join. I really appreciate everyone tagging and tweeting and sharing our hashtags today. It's been an absolute pleasure of mine to chair today and take you through episode 2. Thank you again for joining us as a wonderful interactive audience, and we hope to see you next time. Thank you for taking part.